Hello, good afternoon. I am going to discuss about fluid characteristics and dimension analysis, and I am Steven Silbrianis Cutad 195666. So first of all, let's define fluid characteristics. Fluid is defined as a substance which can flow. Technically, the flow of any substance means continuous relative motion between different particles of the substance. So there are the types of fluids. But firstly, the term fluid includes both liquid and gases. The main difference between a liquid and gas is that the volume of liquid remains indefinite even as it takes shape, surface, or in which it comes into contact, where a gas occupies complete space available in the container which it kept but have compressible volume. First of all, one of characteristic of viscosity. Viscosity means is the fluid property that determines the amount of resistance of the fluid to shear stress. It is a property of a fluid due to which the fluid offers resistance to flow from one layer of the fluid of another adjacent layer. Or in a liquid, viscosity decreases with increase in temperature. In a gas, viscosity increases with the increase in temperature. So let's go with the density. Density is the mass per unit volume of a fluid. In other words, it is the ratio between mass and volume of a fluid. Then density, if denoted by the symbol slant P, this unit also a kilogram over meter cube. Here's the formula. It is the density equals mass over volume and its unit. Well, since the density is mass over volume multiplied to universal gas constant with the temperature, it can also be written as like this. P is equals, pressure is equals density multiplied by universal gas constant times temperature, since density equals m over b, or mass over volume. Let's go to the specific volume. In thermodynamics, the specific volume of a substance is the ratio of the substance volume to its mass. It is the reciprocal of the density and intrinsic property of matter as well. The standard unit is a cubic meter per kilogram, and this is the unit. And this is the formula, which is a specific volume is equals volume over volume equals mass is equals to a reciprocal of density. So specific volume for an ideal gas is also equal to the gas constant, which is R, the unit, multiplied by the temperature and then divided by this pressure multiplied by molar of that ideal gas. So here's the summary of the formula. Also, typically, the specific volume of a substance is expressed in terms such as meter cube over kilogram, feet cube over pound, feet cube over slug, or milliliter over gram. Let's go to the specific weight. Specific weight can be used as a characteristic property of a fluid. Specific weight, also known as the unit weight, is the weight per unit of volume of a material. The symbol of specific weight is this letter Y, a Greek letter gamma. A commonly used value of specific weight of water on Earth at 4 degrees Celsius is 9.807 kilonewton per meter cube, or 62.43 pound force over feet cube. In fluid mechanics, specific weight represents the force exerted by gravity on a unit of a fluid. For these reasons, units are expressed as force per unit volume. Examples as Newton per meter cube or pound feet per cube. Let's go with specific gravity. Specific gravity is the ratio of a specific weight of a given fluid to the specific weight of a standard fluid. It is denoted by the letter S, and also it is dimensionless, which means it has no unit. Specific gravity is equals S, the specific weight of a given fluid, all over specific weight of standard fluid. Also, specific gravity may also be defined as the ratio between density of the given fluid to the density of a standard fluid, or S, or the specific gravity, since it has no unit, is equals density of a given fluid over density of standard fluid. Let's go to the dimensional analysis. Dimensional analysis is a means of simplifying a physical problem by appealing to the dimensional homogeneity to reduce the number of relevant variables. In this case, the analysis involves the fundamental units of dimensions like MLT, means, mass, length, and time. It is helpful in the experimental work because it provides a guide to factors that significantly affect the study phenomena. Also, there are 5 to particularly useful for. Another characteristic of dimensional analysis is there is 2 methods to do dimension analysis. One is the Rayleigh method, while the other one is the Bucking-Pais method. And these are the quantity, the common symbol, and dimensions, and the name for each geometry, kinematics, dynamics, and the fluid properties of their symbols and their quantities and then dimensions. And this is for the fluid properties. Here's for geometry, kinematics, dynamics, and fluid properties. Yeah, everything is in there. So move on. Now let's go to the Rayleigh's method, the first for the dimension analysis. An elementary method for finding a functional relationship with respect to a parameter in interest is the Rayleigh method. This form of dimensional analysis expresses as a functional relationship of some variables in the form of an exponential equation. It was named after Lord Rayleigh. I wrote all the dimension analysis according to its expression. After that, I wrote the expression of the function and the general function, and I write all of the equation, the mass, length, and time, and I use for B and A for the equation 1 and 2, and after that I substitute the first one and second equation into L, which I concluded here, and get the D. After I get the D, I go back to the main equation, this one, and substitute all the drag force of the formula. After that, here I substitute each of it. After that, I cancel, and I obtain 1 is equals to 1, since they have the same left and right handed sign of unit. Now, to the last one is the Buckingham's pi theorem method. Buckingham's pi theorem states that if there are n variables in a problem and these variables contain m primary dimensions, for example mass, length, and time, the equation relating all the variables will have n to m dimensionless groups, dimensionless which means they have no unit. But then, Buckingham referred to this group as pi groups. The final equation obtains the form of pi 1, 2, 3, and so on and so forth. So we have 2 conditions in this method. One each for the fundamental dimensions must appear in at least one of the m variables. The second, it must not be possible to form a dimensional group from one of the variables with a recurring set. Now we are going to apply the Buckingham's pi theorem method. So unit. So first of all, I identify the relevant variables of each unit, and I then write down the dimensional. Step 3. Establishing the number of the independent dimensions and non-independent dimensions group. So step 4, amount of dimensional into independent scaling variables. So I choose m is equals to 2. Example, length and modulus were chosen. For step number 5, create the pies by non-dimensions using the remaining variables. For this example, I used the tip deflection, the I, and W. So pi 1, from this equation, I substitute this one from its dimension, and after I get the AB. From M and L, I get A is equals to -1. From pi 1, the final conclusion is the tip deflection of L raised to -1 is equals pi deflection over L. So, and the same as pi 2 and pi 3. For the last step, for the step 6, set out the non-dimensional relationship. So which is first the pi 1 equals functional of pi 2, comma by pi 3. So and to that I simplified it from this, and the conclusion I cross multiplied, and then this is the final answer, and this is as far can Buckingham's pi 3 can take us, and that's the end. Thank you so much. for listening.